Okay. Okay, okay. Ah, okay, yeah. Now you hear me even better. Okay, sorry about that. Yeah, well, they are, as I was saying, black holes in four-dimensional general relativity turn out to have vanishing Love numbers, which is a rather intriguing property. And as we have just mentioned, I would like to remind that these are also interesting quantities in ADS CFT or ADS like in the correspondence with condensed matter theory. There are several things that could be done that still haven't been done. But here in this talk, I'm interested on understanding a bit better these intriguing properties of four-dimensional, like on the static response of four-dimensional black holes. So we know that these love numbers of black holes vanish, but we also know that these are a very fragile property, actually. Indeed, if one considers minimal modifications to general relativity, some authors, here I'm just writing down some of the first ones to look into it, because there have been many others afterwards, they realize that this property ceases to hold. So love numbers do not vanish anymore as long as one moves a bit farther from general relativity. So a natural question that one may have is, okay, then, let me just, no, shall I ignore it? Or, so what's, okay, sorry. So what is the issue? Okay. Well, good. So within general, one may wonder then, in general relativity, what shall I do to a black hole? Is there something that I can do to a black hole within general relativity in order to excite some modes of polarizability, right? Can I get some non-trivial response from a black hole within general relativity? Well, if we want to answer this question, first of all, an observation that we should point out is that this vanishing of the static response of black holes, four-dimensional black holes in GR, is not something specific to gravity. I mean, love numbers vanish, but also electric polarizability, magnetic susceptibility, scalar responses vanish in four-dimensional black holes of vacuum GR at least. So if we want to answer this question, then we should also answer it for matter fields, not only for gravity. So what are the situations that, without going away from GR, we can consider? Well, from high energy physics, of course, one natural way is letting the dimension be larger than 4. And since we have to answer this question also for matter fields, and high energy physics suggests the presence of light gauge fields, so we should consider some of those. And to be even more general, we can even let the black hole be charged under these gauge fields. So the task of this talk is trying to answer this question by doing a very simple thing, which is just going and doing the computation. So taking, oops, why it didn't change? Yeah. Oh, it just locked me out. Oh no. No, this Zoom link. I think that the connection is a bit unstable. I think this much I can do because it's just not. Yeah, I think it's a connection, but the Wi-Fi is working well, so I don't understand. No, it doesn't. It's not working well for me. That's what. So unless. Okay. Perfect. That's okay. Let's do that. Let's do that. Okay. So where are the slides? Here. What is this? Shift. What is this? Ok. What? What is the problem? Yeah. Yeah, now I have connection, but maybe it's unstable or something. Yeah, I know, but it's not. Why is nothing is working? Let me take it out and put it on again. What is the problem? Yeah, I mean, where's the key? Oh. What is wrong? I've never been. Yeah. No, like here. Here. I mean. The hard disk. Yeah. No. What is wrong? Not understanding. Well, it seems that now this is working, no? So let's try to continue. Yeah. Okay. Okay. Let's hope that this keeps working. So yeah. So as I was saying, we will try to answer this question in a. By just doing the computation, taking a black hole that is charged in general relativity in an arbitrary number of dimensions and study what is the static response of that. So we'll just go and do the computation. So I will. The talk is organized as follows. So first, I will tell you which is the black hole that I'm gonna the kinds of black holes and theories that I'm gonna consider. Then I will tell you a bit of the details on how perturbation theory is performed in higher dimensions, because it's a bit unconventional, perhaps. And then we will look into the solution for a static response in the tensor and the vector sector, and then I will conclude. So the theory I will consider, we will keep the story as simple as possible. We consider Einstein-Maxwell theory in an arbitrary state of space-time dimensions. That's it, where this is the coupling constant, the gravitational coupling constant. That's it. Equations of motion take a super familiar form with the standard energy momentum tensor. And on top of that, we will consider static, spherically symmetric configurations where the gauge field is only electrically charged. In more than 4 dimensions, there are also ways of being charged magnetically or notions of magnetically charged. But we will consider only electrically charged, okay? Just this. So, yeah. The microphone, sorry.
So concerning the motivations, why do you do both charge and higher dimensions? So it's two set of assumptions, right? Why do you do both?
No, but this has a very simple solution, because the group I cited, in particular, together with Luca, they looked into the case for just a neutral black hole in arbitrary number of space-time dimensions. So the idea was to extend that as a black hole is charged and see whether be actually polarized. We will see that in higher dimensions, this is the case. There are modes that do not polarize in higher dimensions, that if you turn on the charge, they polarize. But in 4D, we will see that no.
Yeah, and also, if I may add a comment, it was love numbers has been discussing at a very peculiar quantity. Black holes are very special. So if we have other examples like the one that David is considering, it's important to have other setup that we can understand and
Yeah, so the solutions we consider are just the generalization of Riser-Nordstrom to higher dimensions. So we have the mass and the charge as the only parameters of the solution. The electric field looks like this, where this small n is d minus 2. Okay, so it's just the standard Coulomb law. So very briefly, this solution has 2 Killing horizons. At these positions are plus and are minus, and this has an extremality bound that needs to be respected in order that these Killing horizons are actually an event horizon and a killing horizon protecting a curvature singularity. When this extremality bound is satisfied, well, R plus is the event horizon, R minus the Cauchy horizon. And the last quantity that will play an important role is the Hawking temperature of this black hole. So it is proportional to the difference between the position of the event horizon and the position of the Cauchy horizon. So when these two collide, then the temperature is 0, the black hole is extremal. So let's look into perturbation theory of these spacetimes. No. I'm having the same problem as before. Yeah, I mean, is there, does anyone have another pen drive that for some reason may work? Yeah. Can I have it just here, just in case? Is it working? Okay. So the reason, let me do this, because if I, yeah, okay. Yeah, it's not the most convenient, I'm sorry about this. So the reason, oh no, and this is not the slide, sorry. Yeah, okay, here. So the reason why we are considering a background that is so simple is because perturbation theory in higher dimensions can be only completely understood in particular setups. So we are going to be following what is known in the literature as the Ishibashi formalism. You can think of it as a gauge invariant generalization of the standard Regge-Wheeler-Zerilli approach to an arbitrary number of dimensions. When one takes the dimension to 4, then this formalism becomes becomes a gauge invariant version of the Regge-Wheeler-Zerilli approach. This formalism works in the following situation. The manifold structure needs to be that of a product of a Lorentzian manifold Nm, with dimension m, that I parameterize with coordinates y, and a Riemannian manifold, this calligraphic K with dimension d, n, and that I parameterize with coordinate z. And I will, for simplicity, I will already assume that this compact manifold is maximally symmetric, but it works for any Einstein space, actually, okay? The metric defined on this manifold has the structure of a word product. So we have here the Lorentzian metric on the Lorentzian factor, and then we have the Riemannian metric in the Riemannian factor, in the compact factor, and then there is this word function that depends arbitrarily in principle in the coordinates of the Lorentzian factor. So we want to study perturbations of this. Since the black holes we are considering are charged, we need to consider simultaneously gauge perturbations of the gauge field and also perturbations of the gravitational field. Expanded in coordinates, they look like this, and we see that some of pieces have legs in the compact sphere, other pieces have legs only in the Riemann and the Lorentzian factor, and in the metric case, they can have legs on both. So the following step in this formalism is to decompose the pieces that have legs on the compact space using appropriate theorems. So for a vector field, the theorem we need to use in order to decompose the fields in the compact space is just Hodge decomposition, standard Hodge decomposition. So for the vector field is just the standard version. Hodge decomposition tells us that a differential form can be written as an exact form plus a form that is co-closed. Okay? The co-closed condition means that it is transverse with respect to the covariant derivative on the compact space, and for the metric factor that has only one leg on the compact space, then the same holds. Less conventional result, or less conventional decomposition theorem, is that for the piece of the metric that has both legs on the compact space. This theorem tells us that the metric can be decomposed into a traceless and transverse part that is actually a vector, and then two functions, one that is multiplying the metric on the compact space, and another one that is being hit by a symmetric traceless operator. And they are, like, these pieces are transverse, and this is transverse and traceless, okay? So after this decomposition, we have three sectors. Like, our perturbation variables have three sectors. The tensor sector, which is a piece that has both legs on the compact space, is transverse and it's traceless. Then we have the vector sector that is composed of vectors on the compact space that are transverse. And then finally we have the scalar sector, which are the rest of variables. As you can see, you would expect that the tensor sector is way easier to solve than the vector sector and than the scalar sector in this order, right? And actually in this work, for simplicity, we will just focus on these two sectors. Okay, so the last step in this formalism is to, within each sector, look for solutions that are separable. So all the variables of the tensor sector, I'm going to decompose them into a product of a function that depends, a function or a tensor that depends only on the coordinates of the Lorentzian space, times a tensor harmonic. And the same for the vector variables, so some variable that depends on the, only on the coordinates of the Lorentzian factor times a vector harmonic, and the same for the scalars, where these are the scalar harmonics. So these are three notions that are not distinct in 4 dimensions, okay? So in 4 dimensions, we don't have this sector, the tensor sector, and the vector sector, actually the vector harmonics are given by covariant derivatives of the scalar harmonics and their Hodge duals. Okay, so in 4 dimensions, this is a bit degenerate, but in higher dimensions, they correspond to distinct degrees of freedom. Yeah. Why vector and scalar are related, indeed. Exactly. So then one just goes and takes, when plugging this sort of solution, this sort of ansatz into Einstein equations, then one gets 3 decoupled sets of PDEs for each sector. So we have the tensor variables, vector, and scalar variables, and then one can work per sector because they are decoupled. One goes into a sector, cooks up some gauge invariant variable, and deduces a master equation for it, and repeats the process for tensor, vector, and scalar sectors. Okay, we will do this only, as I said, for simplicity, for vector and scalar, vector and tensor sectors, and we want to investigate in particular static solutions to these equations because we are interested in love numbers. Okay, we want to compute the love numbers. It turns out that for all the equations of the sectors, we are looking at have all of them the same structure. So they can be commented in general. We obtained that the equations governing static perturbations in both vector and tensor sectors are Fuchsian equations, and for generic values of the parameters, this Fuchsian equation is Hoyne's equation that has been commented already in this conference. Let me explain briefly how these parameters depend on the parameters of our background. So the coordinate z that we use in order to write this equation can be thought of as a dimensionless inverse of the area radius. Okay, so it's 1 over r dimensionless. Then the pole structure of this equation is as follows. At z equals 0, we have infinity. What we have is a regular singularity, the regular singularity of Hoyne's equation. At z equals 1, we have the horizon. This is another regular singularity. At z equals zc, we have the Cauchy horizon that induces an extra pole on the equation, so we have 3 already. And then finally, at z equals infinity corresponds to r equals 0, so it's a curvature singularity, but it is not an essential singularity for our differential equation. It's a regular singularity. Okay? So this is the general structure for general values of the parameters, but one needs to look particularly at how the equation, what is the form of the equation when we take particular configurations of the background. In particular, we can look at how this equation behaves when we take the Striemann limit, which is equivalent to sending the temperature to 0. In that case, the Cauchy horizon merges the event horizon, and if we take the opposite limit, the Cauchy horizon merges the space-time singularity. So this would be the extremal limit. And interestingly enough, maybe, in none of this merging of regular singularities of the differential equation, we get an essential singularity. We get, again, a regular singularity. So what we are left with, in these cases, is just the hypergeometric equation. Which is way easier to deal with. So we'll typically solve first for these 2 limits, and then try to see what we can do in the arbitrary charge case, since the Hoyne equation is more complicated. It turns out that the structure of the solutions of these equations are also very similar, qualitatively very similar, so I can talk about them in general. So we are interested in the form of the solution expanded or in a neighborhood of z equals 0, which is infinity, because it's there when we can provide a notion of love number. Okay, so the structure of the solutions of this equation at around z equals 0 is dictated by the roots of the initial equation in that point. In our case, the roots are 0 and 2l plus 1, where this small l is this famous L divided by d minus 3 we have been talking about, okay? So this small l is L divided d minus 3, where this capital L takes values in the natural numbers, and therefore this small l is actually rational numbers. So The general structure of a solution of the equation, therefore, is this one here. The first solution is just the Frobenius solution. It's a solution that is in positive powers of z. So it's a solution that decays at infinity. Okay, it's a regular solution at infinity. Then the second solution has two pieces. The first piece, two pieces that actually will ultimately depend on the values of this second root of the initial equation. It has two pieces. The first piece is this negative power of z multiplied by an analytic function. This means that this solution is not regular at infinity. It diverges at infinity. It can be thought of as a tidal field because of its structure. But it turns out that for some values of this parameter, of this index, then standard theorems of Fuchsian equations tell us that the second solution, in order to be linearly independent of the other one, will contain a logarithmic term. This logarithmic term can be written as some constant times the solution that is precisely the first solution I was talking about, multiplying a logarithm. Okay, so this is the most general solution we can have. So let's see how we define love numbers in this case, or response parameters in this case. The first case to look at is that this is actually an integer. It is actually a generic value. It's not an integer value. Then we know that this solution and the second Frobenius solution are linearly independent. The logarithmic term is not present. Therefore, we can rewrite, well, the usual story. No, we can rewrite this general solution as a global amplitude and a relative amplitude that is multiplying the solution that is decaying at infinity. And once we require that this variable is regular at the horizon, then this number k gets fixed. Okay, that's what we just call the response parameter. That will be a love number whenever this is a gravitational master variable. That will be the electric polarizability when it's the electric field, magnetic susceptibility, and so on. Okay, so far so good. There is no problem with this because this is a generic value. But this doesn't happen in 4D. This also doesn't happen in 5D. In 4D and 5D, L can only take either integer or half integer values, right? So in that case, well, no. Yeah, let's switch to plan B. It works. Okay. So what happens when this parameter actually lies in the natural numbers? This was already addressed by Cole and Smolkin in 2011, and then revisited by Hue and collaborators, in particular Luca, who just gave the talk. And the idea here is that due to the fact that this is an integer number, there is no natural way of distinguishing between one part of the solution and the other. Between this part of the solution, sorry, the decaying solution, and this part of the second solution. There is power mixing. There is no natural way of telling apart one from the other. So one would say that this response parameter is ill-defined, is completely ambiguous. What is not ambiguous is this coefficient in front of the logarithm. This coefficient in front of the logarithm has a nice interpretation as a classical running, as Luca was saying, of this effective action that is written right behind the screen, but I hope you remember. So this is an invariant piece of information. This is as good as much as we can do in these situations in higher dimensions. However, as I mentioned, this is what happens in 4D, and in 4D we don't have these sort of problems. What we have is a remarkable exception in 4 dimensions, which is the following. In 4 dimensions, even though this lies in the natural numbers, the equations are degenerate enough so as to admit polynomials as exact solutions. So this is actually the remarkable property. The parameters are degenerate enough so that this happens. In that case, we can write two distinct solutions, one that is a polynomial and another one that is an infinite decaying power series in Z. But in that situation, when we impose regularity at the horizon, of course, this piece is just a polynomial. It's going to be regular at Z equals 1. So it can only be that this is singular, and therefore that it's not present. Equivalently, if you want, that this k must be 0. So this is what people refer to in this kind of computations as love numbers vanish. In this kind of computations from general relativity, like direct computations from GR. Okay, so every time we have a master variable, we can define response parameters following this definition, this prescription. Okay. So let us look at the solutions for. Let us look at the solutions for the tensor sector. We take the tensor sector that I introduced before. This sector is almost trivial. Actually, it only has this content in the perturbation variables. It only depends on a single function, ht, that is already gauge invariant because of how trivial this is. You cannot even modify this by gauge transformations. By making an appropriate redefinition of the variable and introducing this coordinate z, that is the inverse of the area radius that I was mentioning before, one can obtain a master equation, and one can just try to solve analytically for that response parameter. So looking first at the neutral limit that Hui and collaborators did, one has the hypergeometric equation, so we can apply connection formulas that we know well and obtain exact expressions for the tensor love numbers. They turn, of course, they are organized according to the value of this critical parameter. They are just a number whenever the parameter is different from a half an integer. They have this running problem or this running characteristic whenever it is a half integer, and they are 0 whenever L is an integer because it corresponds in particular to the case of 4D. Also important, although this sector, this tensor sector doesn't exist in the gravitational sector of 4D, of 4 dimensions, we can still take it as the solution of the scalar case in 4D. Okay, so this sector, you can think of it as a scalar perturbation in 4 dimensions. Okay, so what happens if one looks at the extremal case, which when we went to the equations, set the temperature to 0, we got an hypergeometric equation, and it turned out to be almost trivial. The parameters, it is an hypergeometric equation, but the parameters are so degenerate that the solution is just this one you can see in here. So it has a purely just one power that is centered at the horizon, and one power that is centered at infinity. So following the prescription for defining scalar response for defining response parameters, we need to set k to 0 in order to have regularity at the horizon. So we find that in all number of dimensions, for all harmonics, scalar love numbers vanish. Scalar response parameter vanish in the extremal case. So this is quite surprising, at least, well, to say the least, no? And then before commenting what could this be related to, we looked into the, oh, this is not working either, okay. So when looking into the general case of arbitrary charge and arbitrary temperature, even though it's Hoyne equation in principle, we managed to cook up some analytic expression, which was this one. And then we computed the solution numerically, and it matched perfectly, so it had to be the solution. But then afterwards, and Christopher and Daniel pointed out to us that in the particular case of the tensor sector, the accessory parameter satisfies a criteria that tells you that this Hoyne equation in particular, the one of the tensor sector, can be put in hypergeometric form, but only this sector. That's why we were able, even though it was Hoyne equation, to cook up an artisanal solution to this. No? In any case, the expression for the tensor love number is this one. So it's the tensor love number of the neutral case multiplied by this factor that depends on the temperature. And this R plus is just to make it dimensionless. As you can see here, well, I can plot as a function of the charge. So this would be the neutral black hole, this would be the extremal black hole, and I'm plotting the tensor love number for different harmonics. What we see is that, well, this picture is very reminiscent of a sort of an attractor, right? We have love numbers that do not vanish in general unless we set the charge to its maximal value, and then we find that these scalar tensor love numbers vanish. As I already suggested, in my opinion, this is very reminiscent of what is known in and typically known in n equals to d equals for supergravity, the attractor mechanism. So I wonder whether these two issues are related. It would be interesting to look at perturbation theory in those setups and see whether this one is a consequence of the other. So yeah, there's a question.
Question. I don't think it's so much the attractor mechanism, because the attractor mechanism only applies to extremal black holes. So I think it's more that when you approach the extremal black hole, the throat looks like an ADS2 throat, which has the horizon. And as you approach extremality, the horizon goes deeper and deeper and deeper. It's like a trombone. You know, it just goes deeper and deeper and deeper. So in principle, you could you can probably parameterize, and you know, your perturbation essentially, you know, it goes inside the throat, but then it gets killed. It becomes weaker and weaker. When it hits the horizon, then it just, you know, excites it much, much less.
It's too far, no?
And it's
yeah, but this intuition is not correct because of the following result that you will see. If this intuition were correct, then I could apply the same to the, say, the vector love numbers of the extremal black hole, right? And this is not true. They are not zero.
And they're not zero, okay.
Yeah,
So,
I will show it now. So I
somehow-
agree with you. It's the first thing, like when I saw this, I thought, yeah, of course, it's the infinite distance, blah, blah.
Yes.
But, I mean, you go to the computation for the vector sector, it turns out that not to be the case.
but
It seems to be a property of a scalar, explicitly of the scalar field. That's the first reason why it made me think of the
But
attractor
normally-
mechanism, and
yeah.
the second reason,
Yes, go ahead, go
sorry.
ahead.
And then the second reason is that I agree that the attractor mechanism only works like this, but what does it mean to have vanishing love numbers? Roughly speaking, if you want, that no matter what you do at infinity, that at the horizon things are kind of fixed. There is no response. So this is precisely the attractor mechanism, morally speaking, okay? I mean, it's a bit speculative. But these are the two reasons why I thought of the attractor
no, but I think there
mechanism.
is, again, I think it has to do with the repulsion of your field. So normally, as you approach extremality, again, there's an ADS2 throat, which has, you know, some horizon at the bottom, which becomes longer and longer and longer. And when you have an ADS2 throat, some fields, they hate ADS2. So you bring a field at infinity, it just, you know, decays like crazy. You cannot put perturbations inside the ADS2, you know, you can just show that, you know, there's no perturbation which is normalizable on both sides. It either dies at infinity or dies in the infrared. So essentially, I think it has to do, if you just decompose your fields according to this ADS2 harmonics, then you will see that, you know, the tensor, for example, corresponds to some field which is basically repelled by the throat. So then it has a hard time going in, and then the deeper you make the throat, the less it will go in, and then at some point you just get zero, because, you know, it will just be killed by the ADS2 throat before it reaches the black hole. And maybe the next one will actually be a field which goes into ADS2. Anyway.
Okay. So,
Wait, there's another one.
yeah.
Just a quick question to understand. So this is a special case for this Oin function that you're saying that, is it similar to what happens for the Zerilli equation in 4 dimensions in the static limit? Also there, the equation is an Oin equation, but you can show that you can trade the Oin equation for an hypergeometric equation plus a first order ODE. Is that the same, or is it kind of different?
I mean, it's a bit, you're talking about Chandrasekhar's transformation theory, you know, applying this sort of story.
Well, I'm just
you know,
talking, just look at the Zerilli equation in 4 dimensions in the static limit. I just want to understand if it is of the same type. Or
the honest answer, I don't know.
Okay.
But no, in this case, it's simpler than that, definitely. In this case, literally just making another field redefinition. You don't need a linear combination with no, in this case, it's simpler than that, sorry. Yeah, actually, I know the answer. So, Oscar. Yeah.
The equivalent of the vector perturbations.
Yes.
They are the Zerilli perturbations.
Yes.
So
No,
when you
in this
send
case, it's really the
so you will
Point
answer
function.
his question next,
I know.
right?
Okay. Yeah. The higher dimensional Zerilli equation. No, in that case, it's the Hoyne function. This is what I'm going to do now. It's really the Hoyne function. Well, because so far we haven't had matter, because the matter content, the tensor, matter doesn't source the tensor sector in this theory, because you have a vector only. But in the vector sector, the matter also enters the game and couples to gravity. So one needs to define, let's see if this charges up. One needs to define some combinations between these parameters in order to work out a master variable that satisfies a master equation. And if this thing doesn't charge up, I cannot proceed. And I will, just in case. Yeah, I feel like hitting it actually. So let's see if this oops. Where should I find this? Where should I find the USB? Yeah, me too. That's why.
You want to plug the...
So I should send to you the slides, no? Maybe. No. Ah, okay. Yeah. Sure. Sorry. I think it's okay. Like we can. Yeah, thanks, Luca. Yeah. Put the USB. Well, anyways, no. This presentation. Yeah, this one. Yep. Sure. Perfect. Now share screen, no? Oh yeah. Press. Okay. Okay, so as I was saying, for the vector sector, we now have the couple, that the gravitational part and the electromagnetic part couple in this case. So one needs to work out two master variables that are a linear combination of some gauge invariant functions. This A that is nothing but the vector field, and then this omega is some combination of the gravitational variables. I'm not going to give the details of this. But an important point here is that these master variables are defined only up to their respective global amplitudes, which are two independent quantities. So we have 2 degrees of freedom. They can have arbitrary amplitudes, each of them, which you can think of this as the amplitude of the electric part and the gravitational part. But they are independent quantities. This is important. This is important because now we can, of course, define response parameters for the master variables, but these are just some master variables and that we need to relate now to the actual physical fields in order to be able to tell, to interpret them as responses. So when we reconstruct the actual fields, so the metric and the metric perturbation and the gauge field, we find these expressions there. So of course, the fact that these two quantities are independent, these two global amplitudes are independent, can be rephrased into having a global amplitude and a relative amplitude between these two modes. So this relative amplitude is this big theta, this bold theta I'm writing there, which is free. It's a free parameter. I can set it to anything I want. So actually, I can compute these response parameters for any theta. But there are two natural choices. One is that in which there is no magnetic tide, right? So that the coefficient that multiplies the most divergent part of the magnetic field vanishes. And the other natural choice is that in which the most divergent part of the gravitational current vanishes. Right? This would correspond as having a very massive but neutral field orbiting the black hole, or the other way around, having a massless, strong magnetic field orbiting the black hole. Okay, there are these two different situations, and when one fixes the value of theta according to this, one gets that the other, like we will call like the response parameter, the other part that multiplies the decaying piece of the solution, both for the vector part and for the magnetic part, right? And also they become symmetric under a shift of after changing plus by minus of the master variables. So this is actually Heon's equation. So we did not know until now how to solve it using connection formulas because they are not present in the standard literature of ODEs. So what we did is focusing on the extremal cases first. So if you look at the case of the neutral case that was looked at by the group in New York again, they found that they are in general zero. So they are in general different from zero, but there are some special modes. So even in higher dimensions, there are some modes, both in the gravitational and electromagnetic perturbations. There are some modes that do not polarize, that have vanishing love numbers. Okay, this is the piece of information that is relevant here. So when we looked at the case of the extremal black hole, so we set the temperature to 0, we also get an hypergeometric equation that has an extremely involved dependence on the parameters of the background. But remarkably, it is possible to put all the love numbers in terms of a single quantity that depends on two signs in front of two square roots. This is this S, plus minus and plus minus. I'm not giving it from because it's unilluminating. And the interesting point here is that we find that if we turn on the charge, the modes that were actually not responding originally now do polarize. So if you have the neutral black hole, these modes do not respond. If you have the extremal black hole, these modes give a non-vanishing, a non-trivial response. So it's actually the opposite of intuition, right? Like if one applies naive intuition, then the black hole is super far. It doesn't respond because it's the extremal limit. But actually, it does respond, and it even turns on new modes of polarization. Then for the case of intermediate charges, we did not know about the existence of connection formulas for Heun equations, so we just integrated them numerically, with very simple methods. And we observed the behavior I was referring to, so the magnetic susceptibility turns on, like, and enhances, and the same for the gravitational vector love number. Here in dot lines, I'm showing one of the special modes that are not responding in the neutral case and that are turned on as I charge a black hole, right? In any case, even in the intermediate charge case, it is possible to solve the Heun equation in d equals 4 because it admits polynomial solutions again. One can show that in d equals 4, this Heun equation, even though it's Heun equation, it's not the hypergeometric equation, admits polynomial solutions again that are purely growing. So again, in 4D, these vector and magnetic love numbers keep being 0. So it's really a robust property as long as one stays in GR. It was one of the conclusions. So of course, we are thinking of applying the results by Bonelli and collaborators, the group in CISA. Because many of the expressions that we would need in order to compute how these love numbers, the magnetic susceptibilities, depend on the background parameters analytically. Well, the results can be applied to this, so that we do not need to resort to numerical integration. So just to conclude, we have found that static perturbations are governed by Heun's equation. And for the tensor sector that can be thought of the static response of massless scalar fields, we have found that tidal love numbers are proportional to a power of the temperature. And in particular, this means that they vanish at extremality in all number of space-time dimensions. On the other hand, if we consider the vector sector, we find quite the opposite. As one turns on the charge, not only the modes that were already responsive do polarize even more, but one even can turn on modes that were not responsive by charging up the hole. So that polarization, the polarization in those modes would be a signature of charge. And we keep finding that as one puts the dimensional parameter to 4, the equations are extremely degenerate and admit exact polynomials as solutions. So they have no response. So the response parameters keep vanishing for arbitrary values of the charge. So things that could be looked at in the future is, well, as I was suggesting before, checking whether there is any relation to this attractor mechanism of supergravity, checking to what extent this vanishing of tidal loft numbers is generic at extremality. So what happens if I reach extremality by putting a black hole to rotate very fast instead of by charging it up as much as I can. Of course, now with these results for Hoyne equations that we have, it would be interesting to complete the scalar sector that we thought it would be not very informative because we expected it to work pretty much like the vector one. But just with more horrible equations and resorting to numeric integration directly. Now it is more appealing to look into it and try to obtain analytic expressions for those, and also try perhaps the matching to an effective field theory that in this case the black hole now would be a charged point particle instead of a neutral particle. And well, other things that can be done is studying higher ranks, so differential vector potentials that are of higher ranks because of their interest in high energy physics. And also, lastly, I wanted to say that it would also be interesting to look into new methods for obtaining these loft numbers, because master equations and master variables are a luxury that one has in very trivial configurations. We have methods for dealing generically with perturbations on top of black holes that have been used in the literature in the past. I'm thinking of the covariant phase space. This is the formalism in which the first law of black hole mechanics was derived. And they are identities that hold for every solution of the linearized equations of motion. So these identities may be an alternative way of solving or getting some information about loft numbers whenever master equations and master variables are not available, which is in most of the cases. So that's it. Thank you very much, and apologies for all this trouble with the computer and so on.
Okay, so thank you very much for the very nice seminar. So let's start from questions. Please.
So the vector modes which polarize, they have the same charge as the black hole, right? So in a sense, what you're seeing is not the mode coming into the black hole throat. You're basically seeing the charge of the black hole, which lives outside, hitting the vector and giving you some response. Is that correct? Is it a good intuition?
I don't know. What I can tell you for sure is that the computation doesn't give zero and actually gives the opposite. How to interpret this? Well, it's tricky actually, because I didn't say it, but of course, if I have a charged black hole and I put a magnetic field at infinity, it is going to rotate, no? So, but this is encoded not in the parameters that I'm showing. That's why I choose a particular relative normalization between the vector mode and the gravitational mode at infinity. Right? But yeah, it's tricky. I mean, I don't know if the intuition is correct. It could be.
Otherwise, if you have a black hole which has some charge in some U1, let's say you build your theory in some theory which is, has multiple electric fields, multiple kinds of electric fields. If your black hole has charge in one with one electric charge, if you bring in the other electric charge, I don't think you'll be getting this phenomenon if you have two possible charges, if you're not in pure Einstein.
It's an interesting question, and actually you can approach that in the very theory in which you can study relation to this attractor, because like n equals 2, you can have, well, you have more than one.
Yeah.
No, and you can consider Lagrange with that characteristics. Yeah, I mean, I suggest it's easier to do the computation and just...
No, but I think it's because, again, you have a cloud, so you have an ADS2 throat and you have a cloud, and, essentially the cloud outside from the charge interacts with your vector field and, spits it out and gives a response. But it's not really the deformability of the horizon, I don't think, because the horizon is, deep down the throat, and if in the infinite throat limit, which is the extremal limit,
okay, I understand.
You don't get a response. So in a sense, it's not a response of the black hole horizon to this thing, it's a response of the cloud of electric charge around. That's my feeling.
Okay, but then what is the notion of deformability that you would claim is zero?
Yeah, I would say something with the horizon, but okay.
The moments at infinity, they vanish. So in this case, I think Josef's intuition is correct.
Well, it deforms in the sense that the solution to the perturbation is, of course, non-zero, and therefore you can see what is the change that it induces on the horizon. Is that what you say?
What I'm saying is that the horizon deforms in response to the external field.
But not in response, only because of external field.
In response to the external field, it deforms. But this deformation doesn't change the moment at infinity, where the response is measured. So, so in that case, what happens near the horizon is just a calculational tool, as far as I know.
The idea of all of this is that the mode that is purely growing at infinity is induced by an external universe, like by things orbiting around the black hole and so on. So it's purely due to that. No? So there is no internal response to that. Well, that's the whole point.
So I had a naive question. So there are these Copper-Petro-Majumdar solutions if charge is equal to mass, and you have exact static solutions.
Can you say again, please?
These are Copper-Petro-Majumdar solutions, yeah, where Q is equal to M, and they're all static because electric forces balance gravitational forces. Do they not exist in higher dimensions, or I just don't?
Yeah, they do. The point is, they are like doing perturbations on top of that is
no, but there is I think that it just says that you have exact solutions. You don't need any of this. Basically, you don't need tidal disk. You have exact solutions. Because the whole point of doing this, tidal calculations is to see the response of this black hole on the other black hole. But if you already have exact solutions, you already know the response.
I don't see the relation. Like you have exact solutions, which by the way are very fine-tuned. The ones you're talking.
Well, but Q equal to M is fine-tuned, right? So we are.
So they have the same as multi-center solutions, which are in the same class as the ones which Daniel and I computed the multiples for.
Right.
And the point is, Majumdar-Papa-Petro solutions, they have electric charge and they have mass, and they cancel. So in a sense, the effect of one on the other is
that's exactly TH equal to 0, right? So that's exactly the limit in which case.
But I wouldn't deduce from this that
that means there is no response. And
for the extremal black hole, yes, because in the extremal black hole, when you have two extremal black holes of the same charge and mass, essentially they don't affect each other. The solution just, they just sit next to each other. But
so that would explain why those all vanished, right?
No, I think that's in the infinite throat limit, but that's only for one mode. I think that's just
no, but basically, if you have exact solution, which is basically the individual black holes are not perturbed at all, then there is no response.
Indeed.
A static exact solution.
Two black holes, two extremal black holes next to each other at some distance. Yeah, I think in the infinite throat limit, the infinite throat doesn't get deformed. So, the infinite, you get an ADS2 throat for both, and, essentially the perturbations wash out. So, from that perspective, that's another way to see that in the infinite throat, in the infinite ADS2 throat, one black hole is not affecting the other from the exact solution, absolutely. But again, what is more about this charge effect, which I think happens down the throat. I think it's really from the interaction of the throat to the flat space. I think it's come from it's just my intuition.
So you computed also the odd, the gravitational odd part.
Yeah, of course.
Which is not 0.
Which is not 0. That's why I'm trying to say that. But he suggests that this is not actually a deformability. It's some other.
And when the throat is in the ADS...
No, I understand the argument, but I think that, it could be.
There's a way to check which is very easy. If you just look at the numbers go to 0 in the extremal limit, and compared to the length, we can just look at the decay of the modes, and then you can just see that the mode going down the throat goes like 1/r to some power, and then you can get the love. You can just estimate how your love numbers go down with the length of the throat, and when the length goes to infinity, the love numbers go to 0.
The point is that this is not what happens. No? This is not what happens. No, in the vector sector, it's the opposite. That these parameters grow even.
Yes. No, but again, in the extremal limit, when the throat becomes longer and longer and longer, then clearly there's no. Clearly they should go to 0. There's no way you can deform an infinite throat. Infinite throat is an infinite throat. There's no way to deform it.
But this is what the result is saying.
But I think then it means that you're not deforming the throat. I think it means that you're deforming
Could there be an ambiguity in the definition of love numbers?
It could be. Actually, in this case, most general combination, you're not going to get 0. So, no way that by this ambiguity that you could reach 0. given these results.
No, but
so
it's
0 is particularly the value you cannot get from the
question,
computation.
could this be a gauge artifact if you chose your gauge differently? Because
This is a gauge invariant, everything I did. Like there is no single point in which you lose. Like this one is completely gauge invariant.
Okay.
Okay, another question?
So can you go back to a plot where you were showing the numerical results?
This for the vector sector, no? So this is vector log number, magnetic susceptibility. You know?
Yeah, for the magnetic one, is there a point where they vanish for all L, or just not a resolution?
Yeah, it looks, I mean, since it starts so narrow and then it opens up, I could not put some resolution. But no, they don't cross at the very same point.
Okay.
But that's a good observation. No, they don't.
And just another maybe small question. So can you say it again, what is the reason why you did not consider the even part, the scalar sector?
The point is, so the actual answer is for simplicity, because since we thought there were no connection formulas for Hoyne equations, we thought, okay, the behavior is going to be kind of like at least the results we will be able to provide will be the same ones as for vector sector. So exact results at extremality, and then integrate numerically between charges. And we thought, I mean, this is already captured in the vector sector. So now that we have the possibility of getting analytical results, that is more appealing. And we want to look into it, actually.
Yeah, I'm asking because already for zero charge, the vector and scalar sectors have slightly different features. Some of the lab numbers vanish while the others don't. So maybe it would be interesting.
But that's also the point. The fact that even in the neutral case, some lab numbers vanish is in the vector sector. So it's a magnetic type. That's why we looked into this, because we wanted to see whether by charging up the hole, you could turn on those modes. And this is exactly what we find.
Okay.
It's like these dotted solutions. This one is very small. You don't see it very well, no? But it starts at 0 in the charge case. Then you charge up the hole, and then it gains a bit of response. And then you get here our analytical prediction at extremality. And for the magnetic susceptibility, the same, but more even higher, even larger. Yeah. ADS-CMT, yeah. But well, just the interpretation people were saying. For instance, in Kerr, just four-dimensional Kerr ADS, the Kerr ADS solution, this can be, well, in the literature there are works in which people relate this to having some neutral fluids in the boundary that are evolving in a non-trivial flow. And you can actually define sensible energy momentum tensor for that fluid. You can study quasi-normal modes, which is something that George and Oscar did in the past, these quasi-normal modes of Kerr ADS. So I'm just saying that log numbers of this very same solution could also tell you information about that, just to draw some attention into this, because something that can be done.
Okay, so I think it's time to close the afternoon session, and let's thank our speaker again. And we reconvene tomorrow morning at 9:30. I'm afraid so, no?